Hi, everybody. It's Miss Austin, and I wanted to just cover a few things since I've been gone. I've been trying my best to leave activities that have videos in them so you can watch them if you're lost, but I kind of wanted to recap the last 3 lessons. So if you've been lost and you wanted to just kind of know what the most important things were, and I'm also going to make videos of me doing the homework. Sorry I haven't been there. I should be back Monday. So the first lesson was Unit 2, Lesson 1, and it was called Let's Make a Box. The first 2 lessons in this unit are just real life examples of polynomials, but they're going to keep repeating these ideas through the unit. And so if you want to know what they're talking about, it's a good idea to understand what's going on here. So lesson 1 was about making a box. So I actually wanted to show you what it was. I know there was a simulation in Desmos, but this is what it looks like. Imagine you have an 8.5 by 11 piece of paper, and you cut 1-inch squares 1 by 1 out of the corners. Okay, so I'm actually going to do that for you because I know on Desmos they did it, but it's hard to visualize if you're not doing it. If you can hear my dog in the background, is sad because I won't let him in here when I'm filming. Okay, I'm just cutting out 1 by 1 inch boxes out of the corner of this regular piece of paper. Now, how this becomes a box is I'm going to fold up the edges. Okay, so give me a minute here. Oops. I'm folding up the sides. Right? Now look, it's kind of hard to visualize, but if you look here, I've made an open top box, right? It's like the top to a donut box or something. Let me take the sides for you. Just made one corner. Whoa, I didn't cut that very even. Ooh, Miss Austin didn't measure very good, but you get the idea. Again, what's the point of this activity in this lesson? An example of a real-life polynomial. A polynomial is sort of like in English how you string a bunch of words together and form a sentence. In math, you string a bunch of terms together to form a polynomial. So voila, we have a box. Do you see? Let me zoom out. I won't zoom out. I can lift up here. So see this box? Oh, you're seeing my garbage. Okay. So we now have a box. Then the whole idea, now imagine if I did that all over again, but this time I did 2-inch squares out of each corner, right? I'd cut 2, 2, 2 by 2. And then the whole idea was, how do you find the volume of this box? Okay, so in the lesson they talked about reminding you how to find the volume of something, right? So to find the volume, it's length times width times height. And in that activity, if you did it on Desmos, right? Well, okay, go back to the original piece of paper. If this was originally 11, but I cut off 1 inch here and 1 inch here, okay? And then this was originally 8.5, but I cut 1 and 1. So each dimension loses 2 inches every time, okay? Or I shouldn't say 2. It depends on what you make your cut. I did a 1-inch cut. Now if I do a 2-inch cut, it's going to lose 2, 4. On this dimension, it's going to lose 4 on this dimension. So in that activity that we're trying to get you to realize, okay, so we're going to call this we'll call the 8.5 the length. So before I cut it, it was 8.5 by 11 and there was no height because this is a piece of paper. But when I cut the 1 inch out and I folded those up, look, the height is now 1 inch. I folded that up, and that height right there is exactly 1 inch, but I lost 2 inches off of each dimension. So now this is 6.5 by 9 by I cut 1 inch. And then you would multiply those out to get the volume, which we'll do in a second. If you cut 2 inches, you were supposed to try 4 different ones. If you cut 2-inch squares off of the end, like this, each dimension is going to lose 4 inches. 2, 4, and then this is also going to lose 2, 4. So let's just write that one down. So normally it was 8.5. I'm going to lose 4 inches, so that'd be 4.5. I'm going to lose 4 there, that'd be 7. And I was cutting 2-inch sides. And you were supposed to try a bunch of different ones because we were trying to create the biggest, the box with the largest volume that we could with cuts. And you didn't have to do whole number cuts. Okay? Now, instead of trying every possibility, because what if you did a 1.1 inch cut, a 1.2, a 1.3? It would be nice if we could change this into a rule. Okay, and this is where the polynomial idea comes in. All we're doing every single time, however much I cut out of the corner, right? For example, this was a 1 inch cut. This was a 2-inch cut. This number ends up being the height. So, you could try any different amount you want. So let's just call it X. Whatever I cut out of the corners, you're going to take 2 of those away from this. Visualize it again. If you cut a 2-inch, you're going to take away 2 times. If this was 3 inches, you would take away 3 2 times. So over and over again, you're going to do 8.5 take away 2 times however big the cut is. And then the width is 11 take away 2 times however big the cut is. And the height is whatever this number is right here. Probably should have used different symbols. That means times. The height is however big the cut was. And what do you do with these 3 numbers to find volume? You multiply them together. I'm trying to find the biggest one I can. Why are we doing this? To see what a real life polynomial looks like. So it turns out to find the volume, and you can put these in any order you want. Okay? Length times width times height. You could write it like this. You're going to take this, which is 8.5 take away 2 of the cuts, times the width, 11 take away 2 of the cuts, times the height, which is however big you cut. You could also write it like this. You could put this one in front. All this is 3 different dimensions being multiplied together. Okay? That was the whole point of this lesson, is that you understand what this means. This is length times width times height of a box, an open top box that began from a piece of paper with the corners being cut out. The second part of that lesson asked you to then type this into Desmos and see what is the biggest one you could make. So let's go look. I think this is going to work. I sure hope so. So I'm typing this in. So I've got V of X. Oh, actually, I don't need to type. Okay, back up. Sorry. Desmos doesn't like V. So I'm just going to type it in. I'll do this dimension first. 8.5 minus 2 of how much I ever cut times 11 minus 2 times how much I cut out of each corner times the height is how much I cut out, because that's what I fold up. Now we're going to go over here to the Desmos. It's way, Austin's trying to get a better view of this for you. Let's see. Oh boy, how high up does this go? Okay, so I'm gonna do a better window, 66. So there we go. Okay, so now you can see, and they had you do this in the Desmos activity, right here, that's the maximum volume, which is, so the best volume The biggest volume I can get out of a piece of paper that is 8.5 by 11 is 66.148 cubic inches. And that's by making a cut of 1.585 inches out of every corner. That was the whole point of the lesson. This thing that I typed into Desmos, that's a real life example of a polynomial. It just happens to be a volume application. Okay? So I'm going to stop here so you can pause for a minute if you want to go back and fill in any of the activities from lesson 1. That was the whole point of it. This is just a real life polynomial. When you type in length times width times height into Desmos, allowing for any size cut that you want, you can let Desmos graph that possibility and you can see what the maximum volume is. Now, the only thing that's going to change if you have a different size piece of paper is this number right here, 8.5 and 11. If you have a piece of paper that's 10 by 10, then you would just change the dimensions of the paper. You're still going to keep cutting, right? You're going to subtract 2 of the cuts from each dimension every time you cut. I hope that helped. I'll see you soon.